Okay, 4 o'clock. Welcome back to your favorite class. Announcements. Homework number 4 due to my inbox right now. Right now. Okay. Right. That's on mass moments of inertia, and that's the last topic that we're going to cover for exam number 1. So obviously exam number 1 is this Thursday. I have posted a kind of an instructional guidelines for what you're going to do or how you're going to take the test. I just want to pop those in here really quick. This is a document that's available on Canvas, and I just want to talk over this really quick, how this is going to go on Thursday. All right. Exams open everything. So internet, phone, whatever. I can't police you, so I'm just going to let you do whatever you want. All right. What that means, though, is if you sit down and you're going to try to attack a problem and you don't know how to do that problem, you're going to be in trouble. Because if you're searching around everywhere trying to figure out how to do it for 20 minutes on the internet, you're going to run out of time on the test. So you got to know what you're doing going into the test, even though it's open everything. Don't be comfortable. All right. Be nervous. Okay. Be very afraid. I'm just kidding. Evil laugh. All right. Before the exam starts, so 3:55-ish, get all your workspace in front of you prepared, pencils, papers, calculators, your little brother that's going to help you with the test, whatever. Okay. No, don't use your little brother for the test. Use your older brother for the test. All right. Then you'll join the Microsoft Teams meeting as normal, like you're going to come and attend the virtual lecture. I will not be in this room. I will be administering the test virtually from my house. So if you want to come to this room and take the test, that's fine, I guess. Bring your computer with you. You'll have to attend the meeting virtually. But probably more likely you'll do it at home from your desk or somewhere you're comfortable, the library, whatever. Right. Then turn on your camera so I can see what you're doing. Leave your microphone muted. I have to sort of administer or see what you're doing during the test. I have to make sure that it's you filling out the test, and I want to make sure that it's not, your dad who's a PhD level engineer doing the work for you. Okay. This is an example of some camera shot that might be appropriate. Something that looks like this. This is me in my little spare bedroom office working on my test. All right. I'm going to post it in the exam information tab right at the beginning of lecture. So at 4 o'clock, it'll drop. Go and take a look at that document. There's going to be 5 questions. You'll have 1 hour and 40 minutes to do it. 1 hour and 50 minutes to do it. So 1 hour and 10 minutes. And then that last 10 minutes to email me your solution. So you'll have until 5:50 to execute the test. And then you'll stop. And you have 10 minutes to submit the exam to me once you've completed. And you're going to submit it just like you submit homework. All right. Take pictures, scan it, whatever you do, email it to me. And that'll be that. You don't need to copy the problem statement down. You don't need to put it on your, paper, whatever. Just write number 1 and go to town. Right. That's that. I'll be there in the chat. If you have questions, I will answer them by email, or if you use the chat feature in the Microsoft Teams meeting, that's fine. Questions about how the exam will be executed? Okay. So there'll be 5 questions on the test. I've written the test. I can do it in 33 minutes. I time myself. So I like the 3-to-1 rule. That's a little bit better than 3-to-1. It's like 3.2-to-1. So should have enough time to take the test. But if you don't know what you're doing and you sit down and try to do a mass moment of inertia and you don't know what you're doing, you're going to be in struggle bus. All right. Okay. So with that, you guys know that I have posted some practice problems for exam number 1. I will host a review session virtually tomorrow at 7 p.m., which I will record if you can't make it, where we go over some of those problems. I usually like to have some review with you guys. I don't want to take class time to do it, so I'm going to do it in the evening, 7 o'clock. I will broadcast from my lovely bedroom. And we'll go through some of the practice problems, probably like 1 from each section. Okay. If you feel confident, it's not mandatory. You don't have to come. So don't feel like you have to come. If you feel comfortable with the material and you got other stuff to do, no problem. I won't hold it against you. I will record it. I'll post it to YouTube. And if you want to use it the next day to study with, that's also fine. So that's that. I would encourage you to give the problems a go before that review session or before you watch the video for that review session, just so you kind of have an idea of what's happening there. All right. I will send out an invite to that meeting probably sometime tonight. Okay, other questions? Any questions? Rectilinear motion, not on the test. Okay. Let us continue then with where we left off. All right. So we had finally gotten on to motion in this class. Imagine that, a dynamics class with motion. Oh my gosh. We've finally gotten on to motion, and we were looking at one specific example here, which is talking about one-dimensional rectilinear motion. In this particular example, we had the position of a particular particle as a function of time in one dimension. It's one dimension because it only has sort of like an x-axis, a one-dimensional axis, which is the I hat direction here. And the position along that one dimension is given as a function of time here. So this position vector r is changing as a function of time. And we said that that particular scalar magnitude is this function, which is x of t. All right. And in this particular example, we're looking at the relationship between the position, the velocity, and the acceleration in this general one-dimensional coordinate system by doing derivatives with respect to time and looking at how the velocity goes with time, and also later how the acceleration goes with time. And later on in this particular example, we looked at plotting the position, the velocity, and the acceleration as a function of time, and sort of how the integrals and the derivatives relate to each other through these sort of established relationships that we have between position, velocity, acceleration, and time. So this is kind of where we left off last time. I want to dive in now and sort of slosh around a little bit more in one-dimensional rectilinear motion and kind of finish out the rectilinear motion notes today. Kind of just diving in, doing our rectilinear motion, making sure we got vector math nice and tight, nice and tidy. And we're going to look at a little bit more complicated examples today where position, velocity, acceleration, not necessarily functions of time, but maybe functions of some of those other components and how we might deal with that. Okay, so let's get on with that. Let me make sure I got my notes up here. Okay, let's do it. So that was a nice example, probably the most simple example that we can have, where position is a function of time. We just take the derivative straight up to get velocity and acceleration, and things are all nice and clean. But as I sort of mentioned before, not always is the condition when your acceleration, position, velocities are a function of time. Maybe sometimes your acceleration is a function of velocity, or your acceleration is a function of position, whatever the case may be. You might have some alternate sort of expressions. So let's dive in on what some of those might look like now. All right. So some alternate relationships. So if we're interested in position as a function of time, given acceleration as a function of time, it's kind of the opposite of what we just had. Previously in our example, we had position as a function of time. But now what if we have acceleration as a function of time? So now here's one particular example. Let's say you have acceleration vector as a function of time, which we know is some scalar acceleration value in the I hat direction. This is being very particular about our vector algebra and our vector math, where we have some magnitude and some direction, right? Cool. All right. Say we want position. Say we're after this. All right, well, we know position and velocity has a derivative relationship. We know velocity and acceleration has a derivative relationship. Now we're going to go in the other direction. I just sort of want to hammer that home here. Right. So we know that the acceleration is the derivative of the velocity. Right? Or if we're particular about this, acceleration as a function of time in I hat is the derivative of the velocity as a function of time in the I hat. Or if we're just kind of dropping vector notation now, we're more interested in just sort of these magnitude relationships now. That's what we're going to do. I know it seems like a little redundant to write vector form and then go to the scalar form, but when we're talking in 2 and 3 dimensions, this is going to be an important consideration. Okay, so I'm just getting you sort of primed for that right now. So we know something like acceleration as a function of time is our dv dt. And I'm interested in the velocity, so I want to rearrange and I want to get an expression for velocity as a function of t. And so we can write that the differential velocity dv is equal to acceleration as a function of time dt. It's just bringing kind of this guy over to the left-hand side. And now we just integrate this. So this is more or less the integral of dv is the integral of a as a function of time dt. This is just the most generic way that you might think about this. You can either have definite or indefinite bounds on this. I think, for just clarity's sake, let's put some just generic bounds on this. Just to make this clear, where we integrate our velocity from some initial velocity, v naught, to some final velocity, and I'm just going to keep it generic here, v. And here our integral is with respect to time. So we start at some initial time, we'll call it t0, and go to some final time, t. This would be our most general relationship between velocity and acceleration, but kind of just going the other direction. So here we would end up with this particular integral, first fundamental theorem of calculus. This would be velocity as a function of time minus my initial velocity is equal to this integral from initial time to final time, at dt. If you have constant acceleration was not a function of time, then you can just pull this acceleration out, and that would be like the basis for kind of a typical constant acceleration equation that you might see. So a typical constant acceleration equation might be something like this. You may have seen something that looks like this before in your physics class. And that is, if acceleration is not a function of time, it's just going to kind of fall out, something like that. But here we can't make that assumption. All right. So if I wanted an expression for velocity, given acceleration as a function of time, I need sort of this full-on banger here. Initial time to the final time. Acceleration as a function of time minus whatever my initial velocity is. All right. This is one typical form that you might see for one-dimensional relationship between velocity and acceleration, given velocity given acceleration as a function of time. So if you have this particular function and you know initial velocity, which could be important, then you can determine some function of the velocity as a function of time. All right. So position also follows here. And that like, same idea here is that we have like dx is vt dt. This is coming from this general expression, just rearranged. Could again integrate if we want to integrate this accurately from some initial condition x naught to some final condition x. Again, integrating on time, from some initial time, some final time, of my expression of the velocity, which I have from above here. Yeah, kind of a banger. But just more or less just a son of a two-step integral. It's not a double integral, it's a sort of a two-step integral. So when all is said and done, kind of if you work your way through this guy, your position x at any function at any particular point in time, you're going to have something here like xt minus x naught, but I'm actually going to move the x naught to the other side. Oh, I wrote a minus. This should be a plus. I'm sorry about this. Should be a plus here. Bit of a crazy looking situation here. And this would be your general expression for what is the position of my particle in one dimension as a function of time, given the acceleration as a function of time, some initial velocity condition, and some initial position condition. After all those double and triple integrals, this should be a cakewalk here, right? Only single integrals? Man, I've gone soft on you guys. All right, so that's if you're given acceleration as a function of time. You can do similar things if you have like a crazy relationship between acceleration and position, which could be something like you're approaching a black hole. Or if you thought about trying to escape Earth's gravity, the farther you get away from Earth, the less acceleration you'll have towards the center of Earth. Right. So the farther you are away from the Earth's surface, the less your acceleration due to gravity. So that would be acceleration as a function of position. So here you have your acceleration, not as a function of time, but as a function of position x. Bit complicated here. All right. So we'll recall that we had one of our alternate expressions for acceleration was that acceleration x is going to be equal to the velocity times dv dx. So this is one of our alternate expressions for acceleration from last Thursday. Let's rearrange this. We'll bring all the velocity terms on one side and all the acceleration and position terms on the other. So we'll notice here we just have basically position on this left-hand side, and we have velocity on the right-hand side. So we can integrate now. Integrating over x. So from some initial position x0 to some final position, we'll just call it generally x, of my acceleration, a, as a function of x, dx, equals integrating over some velocity, some initial condition and some final condition v, my v dv. All right, so I'll continue and I'll sort of rearrange again. I'm going to work this guy and sort of bring this over to the left. So here we're going to have something like v squared on 2 minus v naught squared on 2 after my integration. Going to be equal to my integral. Here. So the point is now I'm getting to a point where I can start writing my velocity of my piece as a function of x. I'm getting to a point where I can sort of write, what is this guy? An expression for this guy. After rearranging this, I can kind of bring my 2's to the other side. All this to the 1/2 power. So here's a general expression for your velocity as a function of x, if you know acceleration as a function of x. You would also have to know some initial position, x naught, and some initial velocity. All right, one more step to get position. Ultimately, you want position as a function of time out of this. Which looks a little bit difficult how we might do that. How do I get position as a function of time given initially acceleration as a function of position? A little bit difficult to do. Okay. We know that velocity is time derivative of the position, or dt is dx on vx. A little bit strange. Just rearranging here. But in this situation, all my position information is on this right-hand side, because I can write velocity in terms of position. All my time information is over here. So I can ultimately determine what is my position as a function of time, given this general equation. We'll do an example here in just a second. I know it's a bit ethereal at this point, maybe. Some initial time to some final time. Some initial position, I'm integrating over x, to some final position x. This particular integral would give me the position x as a function of time t. This is how we sort of mesh everything together. So integrating here then, time as a function of x. Okay, it's a little bit strange to think about. Usually we like to think about our position as a function of time. How long does it take for us to get to this particular location? This is a little bit backwards. What location do we reach this time? That's sort of how we have to think about this. What's that? What's that? Yeah, exactly. How many meters do I have to go to get to this time? Strange. Here we have a bit of a tricky integral, but we know that the velocity x can be written in terms of the acceleration, which is a function of position. So here we have some initial position x naught, some final position x, and my expression for the velocity in the denominator, which I have from before, 2 times this integral from initial position to final position x of my acceleration as a function of position plus the initial velocity squared, all this to the 1/2 power dx plus whatever initial time I had. Very, very strange sort of equation. But this is used often in interstellar physics, which I'm sure you guys will all be, working on in the future. You'll all be rocket scientists, right? All right. You'll have a homework problem that deals with this equation. Very exciting. Okay. So that's a little bit of a complicated example. You also might have acceleration as a function of velocity. And again, our ultimate hope is to get position as a function of time from acceleration as a function of velocity. Strange. Remember my acceleration? Looks something like this. Sorry, we're given acceleration as a function of velocity. So you happen to know what your acceleration is as a function of your velocity. That one's a little bit harder to wrap your mind around practically. Where would you have a situation where your acceleration depended on your velocity? Oof, I don't know. Even I can't come up with that one. What's that? Yeah, that's not a bad one. Something that relates to drag, since drag is a function of velocity. The faster you go, the more drag you have, and drag is a force, which could lead to a change in your acceleration. Yeah, I like that idea. So you have some cruising velocity on the highway, and the drag associated with that cruising velocity is a force. It can slow you down acceleration-wise. Yeah, I like that. All right. So now we kind of have two paths where we're kind of roaming down simultaneously. We have acceleration as a function of velocity, and we know that this is my acceleration is dv dt. Can rearrange, get all my like variables on the same side. All my times on the left, all my velocities on the right. integrate from some initial time to some final time. Integrate on the right from some initial velocity, some final velocity. Best we can do here is say something like time as a function of velocity. Plus my initial time condition, T0. Okay. This isn't quite position as a function of time, but we're going to get there. I can simultaneously work kind of a different angle. Remember, my alternate expression for acceleration is v dv dx. Again, I can get all my velocities on one side, all my positions on the other side. So I'll move my dx to the left-hand side, move all my velocities to the right-hand side. It's v times the acceleration as a function of velocity times dv. Bit of a strange expression. Sorry. Integrate. Finally, your position as a function of velocity is equal to this strange looking integral. These are two parametrized equations, which together would give you the position as a function of time. Hopefully you learned about parametrized variables or parametrized equations in your math class, right? A lot of times you might see like x as a function of time and y as a function of time, and you can use that to get like x as a function of y. Hopefully you've seen something like that in calculus. It's a very similar idea here. You have time as a function of velocity, and you have x as a function of velocity. So these are parametrized equations in V. T and x parametrized in V. So can solve together. To get x as a function of t, or t as a function of x. One of those should be manageable. All right, how we doing? Stretched our calculus muscle to its absolute limit. It's doing double integrals, doing triple integrals, doing all this symbolic stuff, blah, blah, blah. All right, let's do a real example here. And we'll use some of this information. All right. You got a position of a particle on a straight line defined by this particular equation. I want to determine the time when the velocity is 0, position and distance traveled by the particle, acceleration of the particle, and the distance traveled between two particular points in time. Then we'll also do another example here when we have acceleration as a function of velocity. A little bit of a weird one. Some like people in that room behind us. I feel like we're like fish in a fishbowl and they're just like watching us. Shouldn't it be like a two-way mirror, you know, where they can see us, but we can't see them? This is a focus group. Tell us about your feelings. I'm going to bring that in here in just a second. Okay, let's work through. Here, I'm given this vector. The position vector here is labeled as x bar. I think kind of worked on calling this r bar and the position vector r, location in space. Defining the position of the particle as r as a function of t. Here is this t cubed minus 6t squared minus 15t plus 40 in I hat. Okay. So we would generally say that like the x position of this particular particle is given by this function, t cubed minus 6t squared minus 15t plus 40. So the question here is, when is the velocity equal to 0? We know that the velocity generally is like the velocity as a function of time here in I hat. This is a one-dimensional problem. We're going to assume that sort of maintaining this relationship. All right. So really the question is, when is the magnitude of the velocity in the x direction equal to 0? So we have sort of this one-dimensional system. You know, like I said, it seems silly to keep making this distinction between the vector and this particular function. But since this is the x component of the velocity, like I said, once we move to 2 dimensions, it's going to have to keep track a little bit more clearly. All right. Well, I know that my velocity here is dx dt, change in position as a function of time. Here, that's the derivative of the function given by my x expression. So that means my expression for velocity as a function of time in this particular problem. Take this derivative here. 3t squared minus 12t minus 15. So I want to know when is this equal to 0. Set the velocity equal to 0 and find t. Use your expression. It's your typical second order polynomial. A lot of methods for solving this. But you could find here that the velocity is 0 for two different solutions, one at -1 and one at 5 seconds. Let's only really consider positive times here. Maybe you can go back in time. If you are, what are you doing in this class? Go save the world or something? All right, there you go. So given this particular motion of this particle as a function of time, it's going to have 0 velocity at a time of 5 seconds here. All right.
I have a quick question.
Quick question in the chat.
Yeah. Do you want us to show the derivation of that, or can you just plug it into a calculator just to get it like a solved function?
The question is, do you need to see the derivation of this? I'm not gonna be picky about that. Just say
Okay.
I plugged it into MATLAB or whatever. I trust that you can solve a second order polynomial. If you want to put opposite of b squared plus or minus square root of b squared minus 4ac over 2a on your test, that's up to you. All right. Part B. This situation here is a little bit more complicated. We want to know the position and the distance traveled by the particle at that time. So we want what is position and total distance traveled over time interval. So if you want to be correct about that, 0 to 5 seconds. All right. I have to make a distinction here. Position and total distance traveled are related, but they're not the same thing. All right. So the position, that's easy. It's just the position at any time t is this expression. So for t equals 5 seconds, then my position vector is just this expression xt plugged in for t. So I know that expression from above, t cubed minus 6t squared minus 15t plus 40. I can just plug that in directly for the value of 5. So here this is 5 cubed minus 6t squared. So this is 6 times 5 squared minus 15t. It's 15 times 6. Sorry, 15 times 5. Plus the initial position, which is 40. Units here are going to be in feet. We're told that in the beginning of the problem. So you can ultimately come up with a position vector working through this negative 60 I hat feet. That's kind of your position vector. I should be more clear about this. So that's pretty straightforward, pretty easy to understand. But now total distance traveled. Okay. So position's easy. It is just whatever it is at that particular time. But the distance is how far you went from where you started. All right. So in this particular situation, we have some position that we're interested in and some starting position. So total distance traveled. Is the position I end up with at time is 5 seconds minus the position I started in. That's an important clarification here. All right. Here I've already calculated this. What is my position after 5 seconds? That's negative 60 feet. Here, I want to calculate what is my position at time equals 0 seconds. Typically, when you have a sort of a position equation that looks like this, you're going to start with an initial position of 0. It's just kind of by convention. But here we see that if I plug in t equals 0, I'm starting at a location of 40 feet. So a little bit of care required here. So here, the total distance traveled is negative 60 feet minus 40 feet. And typically you would want to give the absolute value here. So total distance traveled here, 100 feet. Now you have to be weary here because just because I'm looking at time equals 0 and time equals 5 seconds, and I have information about where the particle is located at time 0 and where the particle is located at time 5 seconds, I know that the difference in the distance between time 0 and time 5 seconds is 100 feet. But what's to say that the particle didn't jump out to 1,000 feet this way and then come back to its final position at t equals 5 seconds? So I need to make sure that there wasn't some motion way out to infinity and then come back to my particular location, because then the total distance traveled would be, you know, I went way out to some location over there and then came all the way back. I'd have to account for all that distance that was traveled between those two different points. Okay. Now, the way that I could determine if I have this like go out really far to infinity or go out to some other location and come back is that if my velocity changes between that time interval. Okay. Since I know that my particle only changes the direction of its velocity at -1 second and at 5 seconds, sort of calculated that in part A, I know that I don't have any like changes in the direction of the velocity between 0 and 5 seconds, okay? So that means that the direction which my particle initially went, it continues on that particular direction and doesn't ever change its particular velocity. And that's because there was no point on the domain of 0 to 5 seconds in which the velocity changes, and we proved that in part A. So since we know from A that the particle only changes its velocity direction at -1 and 5 seconds, that the distance traveled between t equals 0 and t equals 5 has to be the total distance traveled. I'll write that in words. All right. That would be different if my particle went out some very far location, then came back, right? It doesn't do that on this particular domain. It just has sort of this constant directional velocity from one location to the other. All right, let's continue. Part C. Here we want to know the acceleration of the particle at 5 seconds. Okay. Well, the acceleration of the time is just the derivative of the velocity as a function of time. So we can come up with an expression for the acceleration as a function of time, then plug in 5 seconds. So this is the derivative with respect to time of my velocity. I've calculated that, or I've got that expression already. It's all the way back up here. 3t squared minus 12t minus 15. My acceleration as a function of time here, 6t minus 12. Acceleration at t equals 5 seconds is just 6 times 5 minus 12. 30 minus 12 is 18. This will be in feet per second squared. Okay, it's the magnitude of the acceleration in x. I want it to be a little bit more clean about representing this as a vector. My acceleration vector at t equals 5 seconds is 18 feet per second squared in I hat. Okay, last little bit. And this is really where we have to consider this idea of like total distance traveled. Here I want total distance over the time domain 4 to 6 seconds. We know from part B, is it B or no, A? Velocity changes direction at t equals 5 seconds. This is important because at t equals 4 seconds, my particle is traveling in one particular direction, okay? Whatever direction that is. Then at time equals 5 seconds, my particle is, approaching a slowdown at 5 seconds and is covering some distance and then at 5 seconds, it turns around and goes the other direction. I need to account for all of the distance that the particle traveled from time equals 4 seconds to time equals 5 seconds, plus the amount of distance that the particle covered from time equals 5 seconds to time equals 6 seconds. If I just considered the positional difference between time equals 4 seconds and time equals 6 seconds, that wouldn't give me the full picture on how far the particle or how much distance that particle covered in that time, because it's not accounting for the idea that the particle went out during the interval t equals 4 to 5 and came back over the interval t equals 5 to 6. So here, the total distance traveled, because of that sort of positional difference, is the position of the particle at 5 seconds minus its position where it was at 4 seconds, plus its position at 6 seconds, minus its position at 5 seconds. This time, like t equals 5 seconds, is sort of corresponds to either a maximum or a minimum of the position. Okay. We can just calculate this. You just plug this into your expression above. I'll just write it straight away. Here's negative 52 feet. At 5 seconds, we're at negative 60 feet. And at 6 seconds, here we're at negative 50 feet. So you can sort of see by the example here what I mean. If I sort of like consider my position as a function of time, here between the windows of 4 and 6 seconds, here's 5. At a time of 4 seconds, we're at something like negative 52. At a time of 5 seconds, we're at like negative 60. Kind of exaggerating this here. And at 6 seconds, we're at negative 50. So in this window, this particle is doing something that looks like this. Right? It's moving out to a location of negative 60, changing its direction and coming back. So I need to account for the total distance that it sort of traveled, which during the time domain of 4 to 5 seconds, it goes here down, or it moves a distance of 8 feet. And between the time interval of 5 and 6 seconds, it's going to be moving 10 feet. And this is the mathematical expression that's going to capture that concept. So here's your answer. There's a total travel distance of 18 feet in that window. Okay. I know we're beating it to death. Seeing some glazed eyes. Let's take a break. I'll come back at, let's say 5:08. Come back. 4:59, almost 5 o'clock right now. I'll come back at 5:08. This is your MSOE coach? No, not. Oh, okay. I was gonna say that seems like kind of a fireable offense. Like scheduled practice and you just don't show up to it. That's tough. Gotta lead by doing, in my opinion. All right, let's get to it. 508. Back to action. All right, let's try a little bit harder example. So far, been pretty straightforward stuff. Let's try this one. Here's our drag problem. Acceleration given as a function of velocity now. Told some about the initial velocity conditions. Determine all of this stuff. We'll tackle this one at the end. Acceleration. Okay. Let's give this a go. So we want an equation for the velocity of the function as a particle, a velocity of the particle as a function of time. All right. We have acceleration as a function of velocity. So we need to think about an equation that relates acceleration, velocity, and time. Probably be useful here to get us to this end. So the equation that sort of relates acceleration, velocity, and prime in time is simply this guy here, right? Acceleration is the derivative of the velocity with respect to time. But in this particular example, we have acceleration as a function of velocity is dv dt. And if we want to execute or we want to do our integrals properly, we have to get all the like terms on one side and all the other terms on the other side. So in this particular example, we want to get all our like velocity terms on the right-hand side and all our like time terms on the left-hand side. So rearrange. And you're going to have something like dt, which has all the time terms sort of on the left-hand side, is dv on acceleration of the velocity. Right. So let's go with this. We can integrate. And so the integral of my time from some initial time t0 to some final time t dt equals my integral here, the initial velocity to some final velocity. I'm integrating on the velocity. I have this differential velocity dv of dv on my acceleration as a function of velocity, which is negative 0.8 v, given in the problem. All right. We're going to just work through this, and we're going to also make an assumption that the initial time is like 0 seconds. Right? All right. So left-hand side here, we're just going to have t minus t0, or if we assume that the initial time is 0, it's just going to be t on the left-hand side here, is going to be equal to, here we have like a constant 1 on negative 0.8 we can pull out. And then the integration here is the integral of 1 on v dv. Anyone know this integral off top of their head? Integral of 1 on x dx?
Natural log of x.
Natural log. Got it in the chat. You guys too slow here in person. Too slow. All right. Natural log. Very good. So here we're going to end up with what will be natural log of v going from v0 to v. So here we'll have negative 0.8 t equals the natural log of my velocity minus the natural log of my initial velocity. Don't forget about that little initial velocity term. A natural log minus another natural log can be written as the argument of the first term divided by the argument of the second term. This is a valid reorganization of this logarithm. Remember, we're looking for velocity as a function of time. Okay, so a little bit of reorganization here. V on V0 is the exponential negative 0.8 t, or my velocity as a function of time. I'm told in the problem statement that my initial velocity here is 40 inches per second. So here we're going to have 40 exponential negative 0.8 t. Where velocity is inches per second and time is in seconds. Okay, so here's my expression, velocity as a function of time. Well, that's nice. I can now move on to part B pretty easily. And that is, I want to find the position as a function of time. Here I know my velocity as a function of time is the derivative of the position as a function of time. Rearrange. Something like that. My integral here. I'm integrating with respect to time, so my bounds need to be some time condition. And I have my velocity expression as a function of time. So this is going to be 40 exponential negative 0.8 t. This integral shouldn't be, you know, all that horrible for you guys. It's just kind of like e to the cx. Your evaluation. Remember here that my initial time is 0. And with these exponentials, you need to be very, very careful. Okay. That's because e to the 0 is not 0. Okay. E to the 0 is 1. So when you're evaluating this particular integral and you're plugging in this bottom condition for t0, this expression does not go away like many do. Okay. Here we'll make another assumption. That our initial position is 0. And so finally my expression will become okay, so that's plugging in my upper bound here. And don't forget I have to subtract the contribution for when this t0 equals 0. So I have to plug 0 in here. E to the 0 is not 0, it is 1. So I'm going to end up with minus and negative, which will be plus 50 e to the 0. Which here is 1. If you rearrange this a bit, 1 minus e to the negative 0.8 t. Get tripped up by those weird exponentials. E to the 0 is 1. Rawr. All right, let's continue with the problem. We have a part C here. It's kind of the prompt for part C. How long until the particle reaches 50% of its initial velocity? So when is v equal 1/2 v0? So since our initial velocity is 40 inches per second, I want to know when is v equal to 20. Since we're sort of decelerating in this problem, how long until we get to that particular velocity? So recall, we had an expression for our velocity as a function of time. We also, before we plugged in sort of the initial velocity, I mean, you could just do this directly. So what we're looking at here is 20 equals 40 e to the negative 0.8 t. Solve for t. Here, it's going to take you only about a half a second. Okay, finally part D. Similar idea here. But here we're solving, we want a final velocity of 0, given our general expression for the velocity. At what value of t does this actually happen? Okay. Takes an infinite amount of time for this particular thing to stop moving. Okay? So the point is, given this general definition, as long as there's some velocity, it will never stop. It's the idea of like, if you keep cutting something in half, it will never go away. Just keep cutting it in half. How long does it take until you get nothing left? Infinite cuts. So with this definition, you never stop. Just like your pursuit of knowledge, this particle will never stop. Rawr. Okay, questions on this guy? A little bit different feel to it. Acceleration as a function of velocity. All right, last couple of things I want to talk about here. is what happens if you have constant velocity and constant acceleration. You've probably seen, like I said before, constant acceleration equations in your elementary physics classes, constant velocity equations in 1 dimensions in your elementary physics classes. And I just want to sort of hammer those home given stuff that we've talked about with non-constant information. So first, let's talk about constant velocity. Okay. So assume v is not a function of time or position or anything like that. Constant. Just driving down the road on cruise control, baby. Then we know our definition of velocity generally is like dx dt. So rearrange to find x as a function of t. Usually that's what you're after, determining the position as a function of time. So you'd have something like dx equals v dt. Integrate some initial position to some final position. Here, some initial time to some final time of your velocity dt. But here now this is a constant, right? So not a function of time. You can just pull this guy out, right? That leads to probably a very elementary sort of expression for a relationship between position and velocity. If you know that your velocity is constant, you're gonna have something like x minus x0 is equal to velocity times t minus t0. Right. It's like as basic as it gets, okay? Then also, if initial position is 0 and initial time is 0, this just simplifies to the position is just velocity times time, which, you know, duh, okay? Seems like a little simple, a little bit kind of silly to sort of write this down, but I want to kind of show you all angles here of this rectilinear velocity. We can also look at constant acceleration. And this more or less is how your constant acceleration equations from your physics class are derived. Okay. So here, your acceleration is not a function of velocity. Your acceleration is not a function of time. Your acceleration is not a function of position. Okay? Constant. Like gravity, baby. Sort of. All right. There's a couple of ways that we can go looking at constant acceleration. But what we're going to do here is more or less just derive these constant acceleration equations, which you've probably seen before. So we can do that by starting in a variety of places. But let's start with our sort of most generic definition of acceleration, where this is dv dt. Okay, rearrange. It has some integral from initial velocity, final velocity, some integral, initial time, final time. Pulling acceleration out gives us something like this. Very simplistic equation. A lot of times if your initial time is 0, this is usually represented as maybe something you learned in your first physics class, which is the velocity here is the acceleration times time plus your initial velocity. It's probably something that you've seen in like one of your first physics classes. You can sort of continue down the road here. Something like this. Here V is A T plus V0 dt. Evaluated from T0 to T. Yes. Or with my initial time is 0, just typical. Then you get this expression, which for some reason is usually written in this way. Which is probably another constant acceleration equation you saw in your physics class. But you see now why we have this requirement of constant acceleration to make this happen. You can't really do these integrals easily unless you can kind of pull these accelerations out. Okay. Sort of the last kind of derivation that you might see is one that uses the relationship acceleration is v dv dx, one of the last kind of expressions that we had relating position and velocity and acceleration. Integrate. Integrate. E squared on 2 minus V0 squared on 2. A is coming out. Or typically this is V squared equals, sorry, there should be a minus here. V naught squared minus 2A x minus x0. That's probably the last constant acceleration equation that you saw in physics. And this is sort of where they come from. We're not going to do a lot with constant acceleration. I'm assuming you did a lot with constant acceleration already in physics and things like that. So I'm not going to do much of it. Much of what we're going to do for kinematics is going to be with things like acceleration as a function of time, position as a function of time, acceleration as a function of velocity, all kind of that crazy stuff that you know, it's a little less common. All right, we're going to call it today. That'll be it for today. Remember, there's an exam review I'll host tomorrow. Please take a look at the practice problems for the test. And see you Thursday if I don't see you tomorrow.